And today I'm going to tell you about some of the work we've been doing in the context of ferromagnetic materials. And this is joint work with Valery Slastikov, who's my main collaborator on this project from the University of Bristol, and it's actually in Vienna somewhere at this moment. And part of this work was done jointly with Oleg Tretyakov, who is now at the University of New South Wales, and a PhD student, Alexander Kolesnikov from Far Eastern Federal University. So the story I'm going to tell you has sort of two sides. It has a mathematical side and a physical side, and basically we start with the physical problems which are well motivated from applications, and we basically try to do everything we can mathematically, rigorously, but whenever we can't do it, we just do the best we can, and then we use the methods of theoretical physics, and then which in turn pose interesting mathematical problems that can be hopefully addressed further. Okay. The main motivation of my of this study is the questions that appear in the studies of next generation of ferromagnetic materials, and these arise in the applications of the new and emergent field of applied science called spintronics. Spintronics is a discipline of applied science which tries to take advantage take advantage of the spin degree of freedom of an electron in addition to the charge, and combine the electrical manipulation of electrons in the material with that of magnetic manipulation. And recent advances in nanofabrication allow unprecedented precision in producing a variety of sophisticated nanostructures, and we heard already about that in the first talk of this session today. And here is an example of such a structure that is important in the context of magnetic spin transfer torque magnetoresistive random access memories. This is so-called a magnetic tunnel junction pillar. And you can see it consists of many layers of materials, of various materials. Let me just say in a nutshell what this is about. This nanopillar has two important layers, which is this ferromagnetic layer, which is called the free layer, and this other ferromagnetic layer, which is called the reference layer. So the reference layer exists in a fixed magnetization configuration, while the free layer can switch its magnetization state from one magnetization to the opposite magnetization. And so this is a way to encode a bit of information in a single cell like this, and then by passing current through that arrangement, one could even read out the relative orientations of the reference and the free layer, or in fact affect the state of the free layer. And this would then correspond to the read and write operation in a magnetic memory cell. So here you see a cross section of such a material, and basically the point I want to make is that the layers that appear here have thicknesses that are going down in a controllable fashion down to a few atomic layers. So these are really ultra thin, essentially atomically thin layers. Okay, and when the thicknesses of these materials reach these magnitudes, their properties can significantly change, and this is because they essentially become two-dimensional materials, and their properties begin to be dominated by the interfaces with the adjacent materials. And in the context of ultra-thin ferromagnetic films, this gives rise to two interesting phenomena. One phenomenon is the so-called perpendicular magnetic anisotropy, as is well known in metallic ferromagnetic layers. Usually the magnetization vector, which is the characteristic of a magnetic material, it's a vector of fixed length, but which can rotate from point to point in space. So in a typical thin ferromagnetic layer made of a metallic ferromagnet, the magnetization likes to live in the film plane. However, as the thickness of the material becomes comparable to a few atomic distances, the interfacial effects tend to produce an additional anisotropy that makes a preferential orientation of the magnetization out of plane. And so this creates two directions of preferred magnetization, up or down. Okay? And the second important effect that has recently attracted a lot of attention is the so-called spin-orbit coupling, which essentially is something that occurs when a ferromagnetic layer is adjacent to a non-magnetic heavy metal. And this produces an indirect exchange interaction between the spins of electrons in a ferromagnetic layer that somehow produce a tendency of spins to exhibit winding or rotations, spontaneous rotations. And this gives rise to a host of new phenomena, and, and the one that I'm actually going to be talking about is this so-called chiral domain walls. But there are also many others, and in particular, there's a lot of effort currently being expended on the studies of these topological defect structures called magnetic skyrmions, on which we've also done quite a bit of work, but I don't have time to talk about it. So, and also as a consequence, this gives rise to numerous applications in electronics, etc. Okay, so I will, in this talk, I will focus on chiral domain walls, and these are domain walls that have been observed recently in materials with so-called Dzyaloshinskii-Moriya interaction. This is the DMI that will appear will be recurrently appearing throughout my slides. So the Dzyaloshinskii-Moriya interaction is the interaction that favors somehow a rotation of the spontaneous rotation of the magnetization vector in a particular way, and the ferromagnetic layers exhibiting DMI were recently shown to produce what so-called Niel-type domain walls, which means that it's a domain wall where the magnetization is rotating in the plane made of the normal to the film direction and the direction of the wall. So if the wall is here, the magnetization rotates like this. Okay. This is different from the conventional situation where one expects so-called Bloch domain walls, where the magnetization pointing like that rotates in this way, in a divergence-free fashion. And this minimizes stray field interactions that are induced by the magnetization. So in these materials, the DMI appears to win over, and these novel types of walls appear which have a sense of chirality. For example, an up domain here will always be connected to the down domain with the magnetization pointing on average in the direction of the outward normal to the up domain. Okay, so this is a novel type of domain wall, and these walls also have been shown to have surprising characteristics. For example, in a magnetic nanostrip, where normally a domain wall will be just a vertical wall, okay, where the magnetization rotates in a Niel fashion, an application of a transverse magnetic field across the wall, which respects somehow the reflection symmetry of the problem, was shown to generate magnetic domain walls which are tilted. So, and the tilt is basically proportional to the magnitude of the applied field. And this is a rather mysterious phenomenon that we wanted to understand in this work. So my approach to this problem is via the micromagnetic modeling framework, which is a continuum theory of ferromagnetic materials. And this theory starts with the energy that is written over here. It's the energy of a ferromagnetic body. So the ferromagnetic body is characterized by a vector m, which has constant length, but as I said, is allowed to change its orientation. And the energy consists of well, how many? 5 terms, okay? And I'm sorry to say, but all of these terms will be important in our analysis. There's just no way around it, okay? We would like to, of course, simplify as much as possible, but you will see that the simplification of these kinds of problems is indeed possible, but is a non-trivial step in the analysis. Okay, and so I just want you to remember one thing. So we have an easy axis along the normal to the film plane, and I'm going to use the symbol parallel to denote the component which is parallel to the normal. And I will use perpendicular to denote the part of the magnetization vector in the plane, okay? So what do we have here? Well, we have the Dirichlet energy, which is called the exchange, which just penalizes the spatial variations of the magnetization vector. So this makes the magnetization want to be constant in space, plus the anisotropy term, which favors up or down magnetizations, then the applied field effect, the so-called Zeeman energy, then the stray field interaction energy, where essentially it's an interaction between so-called magnetic charges, whose charge density is just the divergence of the magnetization. And this divergence needs to be understood in the distributional sense, so that divergence also includes the contributions coming from the boundary of the three-dimensional ferromagnetic sample. And finally, the so-called interfacial Dzyaloshinskii-Moriya interaction, okay, which is written here, which is actually an integral over the lateral boundary, the interface between metal and ferromagnetic material. Okay, so it's a two-dimensional integral here, and it has this form. And it involves first derivatives of the magnetization. Okay, so there are some characteristic parameter values that are written here, which I, of course, don't want you to memorize. But the important point I want you to take out of this is that this problem is actually also has a significantly distinct spatial scale. So there is an intrinsic length scale associated with this energy, which is called the exchange length, which you get by balancing the stray field and the exchange energy, and that's on the order of 5 nanometers. And then there is, of course, the size of the sample, which we want to be in a nanotechnological applications on the order or less of 100 nanometers. But then there's also the film thickness, which is just, in the case of a monoatomic layer, is on the order of 0.5 nanometer. Okay, so there is a significant disparity between the length scales in this problem, which makes it further complicated. So, to summarize what I already was saying, this is it's a formidably difficult problem to analyze. Okay, so first of all, it's a three-dimensional variational problem, which involves a vectorial quantity, okay? So it's a vector, so the variable in question is a vector. Not only that, there is also a hard constraint in this problem associated with the unit length constraint on the magnetization vector, constant length constraint. Of course, it's a nonlinear, non-convex variational problem, and it gives rise to many local minimizers, for example. And it is also non-local because of the presence of the stray field. It has multiple scales. And something I didn't mention here and won't have time to talk about it, but because of the vectorial nature of the order parameter, one could possibly introduce additional topological constraints to study certain classes of coherent structures in these materials. So it is very nearly impossible to do anything other than direct numerical simulations on this full three-dimensional problem. So one generally definitely needs a set of simplified models that are valid in appropriate parameter ranges, and at the same time captures the physical features of the system in a quantitative approximate fashion. Okay. And the key approach to that is to use rigorous asymptotic methods of calculus of variations to come up with a hierarchy of reduced models which are more amenable to analysis. Okay, so let me first introduce to you how one take advantage of the fact that we are talking about the ultra-thin film materials. It makes sense to assume that when the thickness of the film is much less than the exchange length, that the magnetization vector does not vary much across the thickness of the sample. So formally assuming an ansatz in which the magnetization only depends on the lateral coordinates, but not on the vertical component, one could calculate the energy exactly, and after some rescaling and non-dimensionalization, the energy would appear in this form, okay? And so basically what we have here is we have some sort of a function involving, this is an exact expression valid for any delta, okay? Delta is the dimensionless film thickness, and we have these dimensionless parameters that appear here. And there appears to be a kernel here that is essentially Coulombic kernel. Okay, so one could further simplify this energy by taking advantage of smallness of delta, by passing to the Fourier space and then doing Taylor expansions in the Fourier space and then going back to the real space. We arrive at the following reduced two-dimensional energy, which consists of the two-dimensional exchange, the anisotropy, out-of-plane anisotropy, Zeeman term, now the two-dimensional Dzyaloshinskii-Moriya interaction term, and the stray field energy, which has this form, which consists of the so-called bulk charge interaction energy and the surface charge interaction energy. Okay, and to proceed further, we are going to. I'm going to mention the following fact that. We derived in a joint work with Hans Knupfer, who was supposed to give a talk earlier today, but unfortunately couldn't come. This is a basic fact that, so first of all, this bulk charge term is positive. So if we wanted to do some kind of gamma convergence studies of this energy, we could simply drop this term, okay, and get lower bounds that do not contain the contribution of this term. However, this term is actually negative and needs to be controlled from above in order to do anything about this on a rigorous level. And to do that, there is a following helpful fact that this term, which is nothing but the homogeneous H1/2 norm squared of the out-of-plane magnetization component of the magnetization vector, can be controlled almost by a combination of the BV norm of the out-of-plane component and a little excess exchange energy. Okay, and this is related to this nice observation of this logarithm, so-called logarithmic failure of embedding of the H1/2 norm, H1/2 space into a BV space. But with a little bit of an extra control, one could recover control on the norm, and this is true for any choices of R and L here. And basically, by playing with these the choices of this R and L and using the modica mortal trick on the local terms, one could actually control the magnitude of this term here. And in particular, one could see that if we have a sample who's of moderate size, which means the sample which satisfies the condition that the thickness, relative to the exchange length times the logarithm of the lateral size is not too big, the term that comes from here can be controlled by the BV norm of M parallel and times the coefficient which is small. In particular, for L fixed and delta going to 0, this term disappears, and the stray field does not actually contribute to the energy, except for the renormalization of the coefficient in front of the anisotropy term, which is called the shape anisotropy. Okay, so in the end of the day, the reduced energy that we want to study is this one, which is local but still vectorial, and it contains this DMI term now, okay, which is now something that we want to treat. And if we wanted to analyze one-dimensional domain wall solutions, one way to approach this would be just to write an associated one-dimensional Euler-Lagrange equation to this energy and try to find its solutions. And the equation that you get in this situation is like this, okay, which is a system of equations. And it also contains an unknown factor here, which is the Lagrange multiplier associated with the unit length constraint. So this is still a very difficult system of ideas to study. Okay, well, the physicists say, okay, well, but we have an intuition that in a problem in the absence of the applied field, the domain walls must have a Niel character, which means that we can assume that the magnetization rotates in a plane of the normal to the wall and normal to the film plane. If we do this, make this ansatz, then we can write the magnetization like this. And when we plug it into the equation, to the energy in one dimension, the energy simplifies dramatically and becomes what you see here, okay? And this, of course, this energy is essentially up to this term that can be integrated explicitly, is just a variant of the, Cahn-Hillier type energy, double well potential. And so, one could explicitly solve for minimizers of this energy, and they're given here. And the energy of the wall is evaluating the energy on this profile is given by this number, okay, which is positive as long as the parameter kappa, which is the strength of the DMI, is less than a certain critical value. Okay, well, that's great, but but how do we know that, so we just found a solution to the Euler-Lagrange equation associated with this energy. How do we know that it's a global energy minimizer? And maybe there are other minimizers. Maybe there are other solutions. Is this minimizer unique? Okay, so in order to answer these questions, we need to continue with variational analysis of the energy. And it's quite remarkable that in the case of the energy that I just presented to you, such an analysis can be carried out. And the idea is as the computation is actually quite straightforward. You start with the energy, and the first thing you do is you integrate by parts in one of the terms in the DMI, and you obtain the energy that looks like this. Okay, secondly, okay, you just apply Cauchy-Schwarz on the last term, you obtain something like this. And then you use the standard estimate from below for the Dirichlet energy of a three-dimensional magnetization vector in terms of the out-of-plane component, and you get a bound of this guy with this. Okay, and then we also substitute the unit length constraint here, so we get this term. So now we have an energy, a lower bound, that is in terms of only out-of-plane component of magnetization. And this is actually what I'm going to show, that this bound is tight, that this bound is actually, for the minimizer, equality is achieved on this bound. Okay, and so how do we see that? Well, we just apply the good old Modica-Mortala trick, where we basically complete the square on these two terms, and then we incorporate the DMI term inside. And so this expression here simply equals the expression we have here, which is just kind of a total variation of some function of m parallel plus a square. Okay, so as a first step, we just drop this term and integrate over a finite domain. And then this is, we obtain the bound from below here, and then we remove the modulus. And we can do this as long as kappa is less than this quantity, which is almost equal to the critical value that I showed you before. So for practical purposes, this is always satisfied. And, so we calculate this explicitly, and we obtain some expression which we can integrate. And when we integrate and pass to the limit, we have the bound of the energy by the wall energy, which is exactly this number we got from the Niel wall profile. And therefore, since that was a candidate for a test function, then there are, in fact, equalities everywhere above. And in particular, this square expression has to be 0, which means that M has to satisfy this expression, and it cannot have a component that is deviating from the plane of rotation of the Niel wall. Okay, and so this shows that the unique up to translation one-dimensional minimizer is given by this formula. And this is precisely the physicist's ansatz for the Niel wall. Okay, when we started thinking about this problem, we realized that actually that's not the end of the story, because the Dzyaloshinskii-Moriya interaction also modifies the behavior of the system near the boundaries. And so we looked at the situation of looked at what happens when the problem is set not on a whole line, but on a half line, okay? And in that case, again, one could think of a similar ansatz as in the past, and try to plug it into the equation, see what you get. So you get some candidate for a minimizer, and you want to see if that actually gives rise to a global minimum of the energy. And this can be done in a similar fashion. So we write the energy once again, and using the Modica-Mortolo trick, this gives rise to a formula of this form, where the energy now depends on the value of the angle between the magnetization vector and the vertical direction at the boundary of the sample. Then we can minimize this angle, this function in terms of the angle, and one can again recover the energy associated with what we call an edge domain wall, which is illustrated here. And again, this energy matches with what you get from the ansatz. So once again, this is a global one-dimensional minimizer. Okay, so this is great, but these calculations were actually necessary steps for the analysis of the full two-dimensional problem. And in the two-dimensional problem, we now do the Modica-Mortolo rescaling on the respective terms here, okay? And then in the same rescaling, because the DMI terms are of first order, they need to remain invariant. And so there's no epsilon in there. And then we want to pass to the limit in them as epsilon goes to 0. And the fact that we just obtained global energy minimizers, one-dimensional global energy minimizers, together with all these Cauchy-Schwarz tricks and so on, allows us to obtain a full gamma convergence result, which is as follows. So this energy, gamma convergence in the L1 with respect to the L1 topology to the following energy functional, which is just the edge domain wall energy times the perimeter of the boundary, which in the end is a constant. But without knowing what that constant is, we wouldn't be able to actually identify the gamma limit, because we need to get a sharp constant in the limit as epsilon goes to 0, plus the perimeter of the boundary of the set where m parallel equals +1. Okay, and this is the energy multiplied by the wall energy, one-dimensional domain, interior domain wall energy, plus the usual bulk term for coming from the applied field. So the result is essentially what you would expect for the situation without the DMI, but with a renormalized domain wall energy. Okay, so this is something we were able to prove here. Okay, now going to the situation where, in the presence of the applied field, things become much more complicated. Why? Well, because the Niel wall profile assumption clearly cannot be valid anymore. So what we need to do is we need to, in the context of strips, we need to consider domain walls to be essentially objects which look like curves, okay, that span between the boundaries of the strip, okay. And we want to see which configurations of such curves would minimize the energy when somehow in this Modica-Mortolo type limit. And we know that if there is no applied magnetic field, then the minimizer should be a straight wall running vertically. Okay, but as soon as the magnetic field is applied, remember the rotation here appears like this, but if the magnetic field is applied this way, then the rotation like this is no longer optimal. You may want to develop a little bit of a component in the direction of the magnetic field. So the optimal profiles cannot possibly be Niel profiles. Okay, so what do we do in this situation? So the way we approach it is then we carry out a formal asymptotic analysis by introducing a wall-like ansatz and trying to identify the energy, one-dimensional energy associated with the interfacial energy of these walls. And what we find is that this energy, it turns out to be anisotropic. So this gives rise to the problem of minimizing sets with respect to anisotropic perimeter. Also, in addition, when the applied field is changed, the energy of the edge domain walls in the up and down domains are no longer the same. And so this produces an extra asymmetry between the two parts of the edges, and this gives rise to the problem of a contact line here. Okay? And so how do we deal with all this? Well, let's start with the edge domain walls. So with the edge domain walls, we can write down explicitly the Euler-Lagrange equation, which is a bit more complicated. And the DMI contributes in terms of this boundary condition. But nevertheless, this equation can be explicitly solved. That's the solution. Just an exercise, but okay, so with these kind of constants. And one can identify the energy of edge domain walls to be given explicitly by these formulas. Well, the important point is that they behave like this. Okay, so if we compare the edge domain wall energy with, in the presence of the field to that in the absence of the field, we see these two curves for two different types of walls, you know, like up and down domains. Okay, and what you see is that the difference between the energies of the up and down domain at the edge is actually very well approximated by a linear function. Okay, and so we can basically approximate for fields that are not too large the edge domain wall by a much simpler expression, which is the original edge domain wall we already got, plus some coefficient, which is again explicitly computed here. It looks so complicated, but it really isn't, times the magnetic field. Okay, now for the interior walls, things get a little more complicated because there's no way to solve the Euler-Lagrange equation for the one-dimensional domain walls because it's still vectorial. Okay, so we can't integrate. Nevertheless, we can resort to perturbation expansion. So there are two regimes here. One is that the field is small compared to everything else. And in this case, one can show that by formal asymptotic expansion that the wall energy would be simply the wall energy at zero field minus some coefficient, which is written here, times the magnitude of the field, times the sine of the angle between the wall direction and the x-axis. Okay, and there's another regime which is more complicated when h and kappa are both small, and then similar analysis gives rise to a different expression for the wall energy in the asymptotic, using formal asymptotic analysis. So putting this all together, we end up with an energy which consists of the energy of the interior wall and the edge walls, and if we assume that the curve that is spanned by the domain wall is parametrized in this fashion, so the x coordinate of the wall is a given function u of y is the transverse coordinate, okay, then the energy of the interior walls is just given by the anisotropic perimeter of the interior wall, and we can express the angle that the wall makes with one of the axes via the derivative of u. Okay, so the energy of the interior wall is given by this, and the energy of the edges is given by how much this point is further away than this point. Okay, so the difference in length between these 2 points, and so this is given by the difference, this contrast between the two sides and the difference of that interval. And then one could say, one could ask, what are the energy minimizers in this problem? And this problem can be solved explicitly, and it's well known that the minimizers of this energy with fixed endpoints is a straight line. Okay, so we can then substitute a straight line segment of making angle beta with a vertical axis into this energy and compute the energy and minimize in beta. Okay, then we get some formula, and in the end we get the angle. And these are the two expressions of the angle for two different regimes, okay? They're explicit analytical. And then one could compare this with minimization of the one-dimensional energy done numerically, okay? Believing that this minimization provides the global energy minimizers, we can compare, and you can see that all these dots are just the results of the numerical simulations for different parameters. This is for in physical units, and this is the tilt angle in degrees. And either this or this formula, depending on their range of validity, gives a very good approximation to the energy of the minimizers. And this explains the origin and quantifies the tilt in the chiral walls in the presence of the transverse field. So I'm going to stop here. Let me just put up my conclusions, and thank you for your attention.
Questions? Otherwise, you don't get the video.
Do all the excitations that you spoke about in the beginning naturally fall out of this micromagnetics formalism that you presented?
What do you mean?
Well, like you talked about skyrmions. And
no, they're perfectly captured by the... Well, okay, it depends. So there are different situations when, depending on the scale of the, say, skyrmion solutions, there are skyrmions that exist at the scale of a few lattice spacings, and that surely would need to some sort of a lattice-based modeling, although still some qualitative features of those solutions could be captured by the continuum. But then there are other situations. For example, recently there is a lot of interest in so-called ferromagnetic materials, which has an order of magnitude larger exchange length, where the skyrmions can be observed on the scales of tens of nanometers in radius. And so this is, for these, the continuum is certainly quite appropriate.
But like the topological character of these things.
Okay, well, of course, the topological characterization is intimately related to the continuum nature of the solutions. But of course, when you go from continuum to discrete, there is no longer what is called topological protection, but there are energy barriers that you need to overcome. And these energy barriers, of course, are very high. And so these are, in fact, very long-lived structures.